We're going to talk about first row D block elements. Some things that you should be aware of that are expected. Characteristics of the properties of the transition elements. You should know that they typically exhibit variable oxidation numbers, which just means charges. They can form complex ions, which we'll learn more about. They are colored. This is where the colored compounds come from. And they do exhibit catalytic properties. A lot of transition metals are used as catalysts in industry. Scandium, zinc, not considered to be transition elements. They are in the D block, but they're not considered to be transition, and we'll find out why shortly. Okay. You should remember, and we'll talk about a little bit more, that all transition elements can show an oxidation number of +2, meaning a charge of +2. And then you should be familiar with some common oxidation states of chromium, which is +3 or +6, manganese +4, +7, iron +3, and copper +1. We'll talk a little bit more about why you should remember those. Talk a little bit about the bonding model of metals. Typically, metallic bonding is referred to as the sea of electrons. Remember, metals hold their valence electrons very loosely. Low ionization energies, doesn't take much to take those electrons off of a metal atom. So hopefully you can see why they hold them, why it said they hold those electrons very loosely. So these big silver circles or spheres represent really the inner core and nucleus of the metal atoms. So those are positively charged. And then you have the electrons outside of the core that are really free to move throughout the entire structure of the metal. And that is really what holds them together, that electrostatic attraction between the positive nucleus and inner core and the mobile electrons that are on the outside of those atoms. It also explains the ability of metals to be ductile, meaning because of those mobile electrons, you can shift these atoms within those metals. Okay, so getting back to these D block elements, we're going to look at the first row, or the third period of the D block. We've talked a lot about periodic trends on the S and the P block. The D block does not follow these periodic trends. Remember, these S and P, we go from metallic to non-metallic, okay, for the S and the P. Not so for the D. The D block elements, or the transition elements, have very similar physical and chemical properties. They are a subset of the D block, okay, not including scandium and zinc. And the big deal of why they are transition metals and not just called like D block is that they have partially filled D sublevels in one of its common oxidation states. So that is the definition of the transition element, a partially filled D sublevel in one of its common oxidation states. Physical properties: D block elements are dense, hard, metallic elements. More physical properties: high electrical and thermal conductivity, high melting point, malleable, you can beat them into a shape, high tensile strength, they can hold large loads, ductile, you can draw them into a wire. These are all explained through the strong metallic bonding in that transition metal. The 3D and the 4s electrons are all delocalized, so you've got a lot of those electrons moving, and they form a strong attraction to those positive ions, those inner core and the nucleus of those metal atoms. That large number of delocalized electrons accounts for the high electrical conductivity and the higher density than group 1 or group 2 metals, the alkali and the alkaline earth metals. Typical chemical properties, and these are very important. Variety of stable oxidation states, meaning different charges. Ability to form complex ions, the formation of colored compounds, and again that catalytic activity. If you're asked to list the chemical properties of transition elements, these are what should be listed. So as far as electron configurations of the transition elements, remember most of the 3D elements, the 4s is filled, and then the number in the 3D varies from one element to the next. In both chromium and copper, there is only one electron in the 4s. And this is so that there will be more unpaired electrons in 3D. That increases the stability. Important thing, when any of the 3D elements form positive ions, the 4s electrons are removed first. Although we'll see an exception, but that's the general rule of thumb. So these metals in the 3D group, they can lose different numbers of electrons to form different ions. These ions are all said to be different in oxidation state. Oxidation state just really referring to their charge. Chromium plus 3 has an oxidation state of plus 3. Chromium plus 2, oxidation state plus 2. I have tried to use those terms. Oxidation states of the 3D block. Okay, those 3D electrons shield the 4s electrons, so the first ionization energy is relatively constant across the period. From left to right, meaning from scandium to manganese, the effective nuclear charge is increasing so that the maximum oxidation state is the most stable for the elements on this left side of period 3. What do I mean by maximum oxidation state? It means that all 3D and 4s electrons are lost. Okay, when we go from iron to zinc, that is on the right side of this third period, the plus 2 oxidation state is the most stable. Scandium and zinc. Scandium and zinc don't share all the properties of the transition elements because they do not have a partially filled D block. Zinc always forms that plus 2 ion. It loses those 4s electrons and the 3D is kept full. Scandium always forms a plus 3 ion. It loses all of its valence electrons, the 4s2 and the 3d1. First row, S block metals lose those s electrons easily, but the ionization energy for those inner electrons are high, so that those are never lost. Okay, we're talking about the alkali and the alkaline earth metals. Okay. For that reason, they have the same oxidation state, meaning group 1 is always plus 1, group 2 is always plus 2. The transition metals have slightly higher effective nuclear charge, so that first ionization energy are higher, but there's no sudden increase that we see with the other S block and P block elements. Looking a little bit more at these oxidation states, just trying to point out from scandium to manganese is where we will have maximum oxidation states, meaning losing all of the 3d and the 4s electrons, and then from iron to zinc, really plus 2 is the most stable oxidation state. finally getting to a picture. Sorry, there's a lot of text. We can see the blue spheres represent the most common ion for the third period D block. You can see that the most common is the maximum oxidation state, with some other ions also being common for both vanadium, chromium, manganese. Iron, we see that +2, +3. Cobalt, +2, +3. Nickel, the most common, is +2. Copper, +2. And zinc is always that +2. So it's almost looks like a pyramid, except there's some holes missing here. And this just gives you an idea, a little bit more of a visual, and what the pairing up of some of these transition metals with a highly electronegative atom like oxygen to actually attain that high maximum oxidation state. Okay. We talked about the half-filled sublevels, chromium and copper, affecting the stability of those oxidation states, those half-filled 3D. In manganese, the +2 state has a half-filled, much more stable than the +3 or 4. Iron, the +3 is the most stable, and it has a half-filled 3D shell. The +2 state is quite strongly reducing. We'll see what that means in the Electrochem chapter. And copper +1 exists as a full 3D sublevel, and like Zn +2, its compounds are not colored. Looking at iron +2, cobalt +2, you see that half-filled D block giving stability. So sometimes that 4s electrons are not all lost first.